Okay, so for a half wave rectifier, suppose our input graph is like this. Okay, and after adding the capacitor, our output looks like this. I will draw this in red. Okay, like this. And okay, let me draw another cycle, I guess. Okay, all right. So what is the time period of the ripple? I mean, what is the distance between one upper peak of the ripple and another upper peak of the ripple? What is this distance? This is the time period of the ripple. I will call this TR, time period of the ripple. Well, it is we can see directly from the graph that the distance between two peaks of the ripple is equal to the distance between two peaks of the signal. Okay, this was the peak of the original signal, input signal, and this was another peak of the input signal. So the time period of the ripple is equal to the time period of the signal. So if we okay, so from this analysis we got that the time period of ripple is equal to the time period of signal. So what will be the relation of the frequency of the ripple to the relation of the frequency of the signal? We know that the frequency is related to time period by, if f is the frequency, write that in small font, if f is the frequency, then f equals 1 by t. Okay, so we can say that the time period of so the frequency of the ripple will be equal to the frequency of the signal. Okay, so if we apply a suppose 50 hertz sinusoidal wave to the input of our rectifier, then and we add a capacitor to the output, then then we will have ripples at the output. Then the frequency of the ripple will also be 50 hertz. Okay, so what will happen in the case of a full wave rectifier? Can you guess? Well, let me, I guess I can draw the full wave rectifier in short. Our full wave rectifier was like this. We had 4 diodes like this, and we had an input signal and another 4 diodes, sorry, and the 2 diodes. Okay, yeah, that was our full wave rectifier. So where are we going to add the capacitor for the full wave rectifier? We need to take attach the capacitor to the output voltage. Where did we take the output from? Well, we took the output from these two terminals. So we will attach our capacitor in parallel with the output. Okay, yeah, simple as that. Okay, so we attached the output we attach the capacitor in parallel with the output resistance. So in this case, what will be the output graph? What will the output graph look like? Suppose as before, our input, let me draw the input first. Okay, the input was like this. Okay, another cycle, yeah. Okay, so what will be the output without the capacitor? Without the capacitor, let me draw that in blue now. Without the capacitor, the output was like this. I had the positive cycle would be output as before as the input, and the negative cycle will be flipped. Okay, then this will continue. And the negative cycle will be flipped again. So this yellow part of the graph, this would be the output without the capacitor. Okay, without capacitor. This is for a full wave. Now after we add the capacitor, the same phenomenon will happen, that after we add the capacitor, the output will rise with the input as before, but when the input starts to fall, the output will not fall like before. Okay, the output will not fall like before. The output will be due to the presence of the capacitor, the output will fall more slowly. And then again another charging cycle will begin. Okay, another charging cycle will begin. Sorry for my slow drawing speed, I am not so good at drawing graphs. Okay, and another charging cycle will begin, then another discharging cycle will begin, and you get the idea of what is going to happen. Okay, so if we add a capacitor to the output of a full wave rectifier, what is the time period of the ripple? Okay, what I mean is that what is the time difference between one peak of the ripple and another peak of the ripple? You see, this is the first peak of the ripple and this is the second peak of the ripple. What is the time difference between these two? Okay, so you can see that when the ripple was in the first peak, the second peak of the ripple coincides with the trough of the original signal, and the third peak, the second peak of the original signal is equal to the third peak of the ripple. Okay, so the signal time period was between this peak and this peak. Okay, this was our original signal. You see, our original signal was like this. So how do we calculate the time period of a signal? We take the time difference between these two peaks. Okay, between two peaks or two troughs. Okay, if you can remember from your waves and oscillations course. Okay, so the distance between these 2 points is the time period of the signal, and the distance between these 2 points is the time period of the ripple. This is for a full wave rectifier. So you can actually see that this point, okay, this point is actually halfway between the time period. So we can easily conclude from this graph that for a full wave rectifier, the time period of the ripple is actually half of the time period of the signal. Okay, simple as that. So what is the main difference that we see here? For a full wave rectifier, the time period of the ripple is half of the time period of the signal, and for a half wave rectifier, the time period of the ripple is equal to the time period of the signal. Alright, so if we write this in terms of frequency, what can we write? Well, we know the relation between time period and frequency is the inverse. So let me write that. TR, we can write TR as 1 by FR. FR means the frequency of the ripple, and TS we can write as 1 by Fs. So Fs will be the frequency of the signal, and from this we can write Fr equals to Fs. Okay, all right. So the frequency of the ripple is actually twice the frequency of the signal. Except this, everything is the same as in the case of a half wave rectifier. Alright, so for a full wave rectifier, for a half wave rectifier, we saw that the frequency of the ripple was equal to the frequency of the signal, and for a full wave rectifier we are seeing that the frequency of the ripple is twice the frequency of the signal.